Hello, and welcome to the Drowsy Professor. Tonight, we're going to explore one of the most fundamental forces that shaped our universe and everything you see around you: light itself. As you settle in for this gentle journey through science and wonder, let me know where in the world and at what time you're watching. Now, get comfortable, take a slow breath, and let's begin our exploration of how light built the world you see. In the beginning, there was darkness. Not the familiar darkness of a moonless night that you might experience in your own world, but something far more profound. A darkness so complete that the very concept of light had not yet come into being. Picture, if you will, the universe in its earliest moments, a place where time itself was barely a heartbeat old, where space was compressed into dimensions so small that nothing you could imagine from your everyday experience would make sense. It was in this primordial realm, just a tiny fraction of a second after the universe began its expansion, that the first photons came into existence. These weren't the gentle rays of sunlight that might stream through your window on a peaceful morning, or even the soft glow of starlight that decorates your evening sky. These first photons were born in conditions of unimaginable energy and heat, emerging from a cosmic soup where matter and energy danced together in forms that would seem almost magical if you could witness them today. Imagine the temperature of this early universe. Not the warmth of a summer day or even the heat of a blazing fire, but temperatures so extreme that atoms themselves could not exist. In this environment, particles of matter and their antimatter counterparts were constantly appearing and disappearing, while photons of light carried energies that dwarf anything we encounter in our modern world. Yet, even in this chaos, there was a certain peaceful rhythm to the process, like a cosmic symphony playing out on scales of time and space that stretched beyond human comprehension. As the universe continued to expand and cool, these first photons began their journey through space and time. Think of them as tiny messengers carrying the story of creation itself, each one a perfect packet of energy that would travel potentially for billions of years before encountering anything substantial enough to stop or absorb it. In those earliest moments, the universe was opaque to light. The photons would travel only tiny distances before colliding with the dense soup of particles that filled all of space. Picture this early cosmic environment as similar to being inside a thick fog on a winter morning, where light exists but cannot travel far before being scattered or absorbed. The photons would bounce from particle to particle in an endless dance of absorption and re-emission, creating a kind of cosmic glow that permeated everything but could not escape to travel freely through space. This period, which scientists call the radiation era, lasted for hundreds of thousands of years, a time when light existed but could not yet illuminate the universe in the way we understand illumination today. During this long period of cosmic evolution, something remarkable was happening to these photons as the universe continued to expand and cool. Like an orchestra gradually tuning itself before a performance, the chaotic energy of creation was slowly organizing itself into more stable forms. The extreme temperatures that had prevented atoms from forming were gradually decreasing, and the density of matter that had trapped light in its endless dance of scattering was slowly thinning as space itself grew larger. You might imagine this process as similar to watching a thick morning mist gradually clear from a valley, revealing more and more of the landscape below as the fog dissipates. The universe was becoming transparent, and for the first time since the earliest moments of creation, photons would soon be able to travel freely through space without constant interruption. This transformation wasn't sudden or dramatic. It unfolded over thousands of years with the gentle patience that characterizes so many of the universe's most profound changes. As the cosmic temperature dropped to levels that would still seem incredibly hot by earthly standards, about 3,000 degrees Kelvin, similar to the surface of a red giant star, a critical threshold was reached. At this temperature, electrons and protons could finally combine to form the first hydrogen atoms, the simplest and most abundant elements in the universe. This process, known as recombination, marked one of the most important moments in cosmic history, though it happened with such gradual gentleness that no dramatic explosions or violent events marked its passage. Picture this moment of recombination as the universe taking its first clear breath. As electrons settled into stable orbits around protons, creating neutral hydrogen atoms, the cosmic fog that had trapped light for hundreds of millennia began to clear. Photons that had been trapped in the endless dance of scattering could suddenly travel freely through space for the first time. The universe became transparent, and light was finally liberated to begin its epic journey across the cosmos. This moment, occurring roughly 380,000 years after the universe began, marked the birth of what we now call the cosmic microwave background radiation, the afterglow of creation itself that still permeates every corner of the universe today. These ancient photons, stretched and cooled by billions of years of cosmic expansion, continue their journey through space even now, carrying with them the fossil record of the universe's birth. On quiet nights, when you look up at the dark spaces between stars, a tiny fraction of the static you might see on an old television set comes from these very photons that have been traveling since the dawn of time. The liberation of light marked the beginning of what astronomers call the cosmic dark ages, a period when the universe was transparent but had not yet formed the first stars to illuminate the cosmic landscape. During this time, which lasted for several hundred million years, the universe was filled with vast clouds of hydrogen gas floating in the darkness, slowly stirring under the gentle influence of gravity's patient pull. These gas clouds were not uniform, but contained tiny variations in density, some regions slightly denser than others, some slightly more sparse. Imagine the universe during this time as a vast, dark ocean with gentle currents slowly moving through its depths. The liberated photons from recombination provided a faint background glow, but there were no stars, no galaxies, no other sources of light to break the cosmic darkness. Yet within this apparent emptiness, the seeds of all future illumination were already being planted as gravity worked its slow magic on the floating hydrogen clouds. Over millions of years, the denser regions of hydrogen gas began to attract surrounding material, growing slowly larger and more massive. This process happened with extraordinary gentleness. There were no sudden collapses or violent events, just the patient accumulation of matter as gravity drew gas clouds together. As these clouds grew more massive, they also grew denser and hotter, like a slowly tightening embrace that gradually increased the pressure and temperature at their centers. Picture these growing gas clouds as cosmic nurseries where the first stars would eventually be born. The process was so gradual that millions of human lifetimes could pass without any visible change, yet the inexorable pull of gravity continued to draw matter together, concentrating it into smaller and smaller volumes. As the centers of these clouds grew denser, the gentle warmth created by gravitational compression began to heat the hydrogen gas to higher and higher temperatures. When the temperature at the center of these collapsing clouds reached about 10 million degrees Kelvin, something magical happened. The hydrogen nuclei, compressed and heated to extraordinary conditions, began to fuse together, combining to form helium and releasing tremendous amounts of energy in the process. This nuclear fusion created the first light sources since recombination. The first stars had been born, and for the first time in hundreds of millions of years, the universe had new sources of illumination. These first stars were unlike any stars you might observe in your night sky today. They were massive giants, perhaps 50 to 100 times more massive than our sun, burning with incredible brightness and intensity. Yet even these stellar giants began their lives gently, with nuclear fusion starting as a small glow at their centers and gradually building to the brilliant illumination that would eventually shine across vast distances of space. Picture the moment when the first star began to shine as the universe lighting its first candle after eons of darkness. The light from this stellar pioneer began to travel outward in all directions, carrying photons that would journey across space for millions or billions of years. Unlike the trapped photons of the early universe or the fading glow of the cosmic background radiation, These new photons carried the energetic signature of nuclear fusion. They were starlight, the same type of illumination that would eventually make possible all the wonders of the cosmos. As more and more of these first stars ignited across the universe, they began to transform their cosmic neighborhood in profound ways. Their intense ultraviolet light had the power to strip electrons from hydrogen atoms, reversing the recombination process that had made the universe transparent. This reionization of hydrogen created glowing bubbles of ionized gas around each star, like streetlights creating pools of illumination in the cosmic darkness. The light from these first stars also began to affect the formation of future generations of stars. The energy they released heated surrounding gas clouds, sometimes preventing them from collapsing to form new stars, while their stellar winds pushed material around, creating new patterns of density that would influence where and how the next generation of stars would form. In this way, light itself became an architect of cosmic structure, shaping the universe through its gentle but persistent influence. These stellar pioneers lived fast and bright, burning through their nuclear fuel in just a few million years before ending their lives in spectacular supernova explosions. But even these cosmic fireworks, violent as they were on astronomical scales, contributed to the gentle transformation of the universe. The explosions scattered the heavy elements created in stellar cores across vast regions of space, seeding the cosmos with carbon, oxygen, silicon, and iron, the building blocks that would eventually make planets and life possible. Picture these supernova explosions not as destructive events, but as cosmic gardeners, spreading fertile material throughout space where it could nurture the growth of new stars, planets, and eventually the complex chemistry that would lead to life itself. The light from these explosions carried news of stellar death and rebirth across the universe, traveling for billions of years to reach distant corners of space with its message of cosmic recycling and renewal. As the first generation of stars lived out their brief but brilliant lives, their legacy was the transformation of the universe from a simple place filled only with hydrogen and helium into a more complex realm enriched with heavier elements. The second generation of stars that formed from this enriched material were different from their predecessors, smaller, longer-lived, and capable of supporting the formation of planetary systems where rocky worlds could condense from the stellar debris. The light from these second-generation stars was also different, carrying in its spectrum the signatures of the heavy elements created by previous stellar generations. Astronomers today can read these stellar spectra like cosmic genetic codes, tracing the ancestry of stars and understanding the chemical evolution of the universe through the subtle fingerprints that different elements leave in starlight. This ongoing cycle of stellar birth, life, death, and rebirth created an ever more complex and interesting universe, with light serving as both the driving force and the messenger that carried information about these transformations across vast distances of space and time. Each new generation of stars added to the cosmic library of elements while spreading their illumination farther into the darkness, gradually creating the richly structured universe we observe today. The photons from these early stars are still traveling through space today, some of them destined to arrive at Earth as the faint light we detect from the most distant galaxies. When astronomers point powerful telescopes toward these remote regions of the universe, they're literally seeing the light from some of the first stars that ever shone, photons that have been traveling for over 13 billion years to reach our instruments. Picture these ancient photons as time travelers carrying news from the universe's youth, each one a messenger that can tell us about conditions in the cosmos when it was less than a billion years old. The fact that we can still detect and study this ancient light represents one of the most remarkable capabilities of modern astronomy. The ability to use light itself as a time machine that allows us to observe the universe as it was in its earliest years. As you rest here, contemplating this vast cosmic story, consider that the light entering your eyes right now connects you directly to this ancient chain of illumination that stretches back to the universe's birth. The photons that allow you to see these words carry the same fundamental properties as those first liberated photons from recombination. And the nuclear processes powering the light by which you read are descendants of the fusion reactions that lit the first stars. The gentle rhythm of stellar birth and death that began with those first massive stars continues today in the galaxies scattered throughout the observable universe. New stars are forming constantly, their light adding to the cosmic glow that has been building for over 13 billion years, while older stars continue their patient burning, converting hydrogen into heavier elements and energy in the same fundamental process that powered the first stellar pioneers. In this way, the first photon's journey represents not just a single moment in cosmic history, but the beginning of an ongoing story that connects the universe's birth to the present moment and extends into the far future. Every star that shines today, including our own sun, is part of this cosmic legacy of light that began when the universe first became transparent and the first stellar furnaces ignited in the primordial darkness. Tonight, as you prepare for sleep, you can take comfort in knowing that you are part of this vast, luminous community that spans the entire universe. The same nuclear processes that powered the first stars continue in our sun, providing the energy that sustains all life on Earth. The light that warms our world and makes vision possible is part of an unbroken chain of illumination that stretches back to the cosmos's very beginning, connecting each of us to the grand story of how light built the world we see. As billions of years passed and the universe continued to fill with the light of countless stars, something remarkable began to happen on at least one small, rocky planet orbiting an ordinary yellow star in the outer regions of a spiral galaxy. Here on Earth, the gentle rain of photons from our sun began to interact with matter in ways that would eventually lead to one of the most extraordinary developments in the history of life. The evolution of vision itself, the ability to detect and interpret light in ways that would transform how living beings experience their world. Picture our planet in its earliest days, roughly 4 billion years ago, when the surface was still cooling from its violent formation and the atmosphere was filled with gases that would be toxic to most modern life forms. The sun shone just as it does today, sending its steady stream of photons toward Earth. But there was nothing here yet that could truly see this light. No eyes to appreciate a sunrise, no vision to distinguish the blue of sky from the gray of clouds. Yet even in this apparently lifeless world, the foundations for sight were already being laid through the patient work of chemistry and evolution. The first living things on Earth were simple, single-celled organisms floating in the ancient oceans, creatures so small and basic that they possessed none of the complex structures we associate with life today. They had no eyes, no nervous systems, no brains to process information about their surroundings. Yet even these primitive beings were not entirely blind to the light that bathed their world. Some of them contained molecules that could interact with photons in simple but meaningful ways, absorbing light energy and using it to power basic chemical reactions. Imagine these early microorganisms as tiny living laboratories where the first experiments in light detection were taking place. Some bacteria developed the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into the sugars that fueled their growth. This process required specialized molecules called chlorophylls that could capture photons and channel their energy into chemical reactions. While this wasn't vision in any sense we would recognize, it represented the first time that living things began to respond specifically and beneficially to light. Other early organisms developed different relationships with light. Some learned to move toward areas where light was brighter, following gradients of illumination toward the surface waters where photosynthesis was most efficient. Others discovered that they could avoid the damaging effects of too much ultraviolet radiation by moving away from the brightest light. These simple behaviors required the ability to sense light intensity, even if only in the most basic way possible. The molecular machinery that made these early light responses possible was remarkably elegant in its simplicity. Certain proteins could change their shape when struck by photons, triggering chemical cascades that affected the organism's behavior or metabolism. These light-sensitive proteins, called photoreceptors, were the ancestors of all the sophisticated vision systems that would eventually evolve, but in their earliest forms they could do little more than distinguish between light and dark, or perhaps detect whether light was getting brighter or dimmer. Picture one of these ancient bacteria floating in the warm shallows of a primordial sea. Its simple photoreceptor molecules responding to the changing intensity of sunlight as clouds passed overhead or as the organism drifted deeper into the water column. There was no consciousness here, no awareness of seeing in any meaningful sense, just the automatic chemical response of molecules designed by evolution to react to electromagnetic radiation in ways that help the organism survive and reproduce. Over hundreds of millions of years, these simple light-sensing capabilities gradually became more sophisticated through the slow and patient process of evolutionary refinement. Random mutations in the genes that coded for photoreceptor proteins occasionally produced versions that were slightly better at detecting light, or that could respond to different wavelengths, or that were more sensitive to small changes in illumination. Organisms that inherited these improved light sensors had advantages in finding food, avoiding predators, or locating suitable habitats, and so these beneficial mutations were passed on to future generations. As single-celled organisms evolved into more complex multicellular creatures, their light-sensing capabilities evolved as well. Instead of having photoreceptor molecules scattered randomly throughout their bodies, some organisms began to concentrate these light-sensitive proteins in specific locations. This represented the first step toward the development of true visual organs, structures specifically designed for detecting and processing light information. The earliest of these proto-visual structures were nothing more than simple eye spots, small patches of light-sensitive cells clustered together on the surface of primitive animals. These eye spots couldn't form images or distinguish shapes. They could only detect the presence or absence of light, and perhaps determine roughly which direction light was coming from. Yet even these simple capabilities provided significant survival advantages for the creatures that possessed them. Picture a small, soft-bodied worm-like creature crawling across the sandy bottom of an ancient shallow sea, its primitive eye spot detecting the shadow of a larger animal passing overhead. The sudden darkening triggers a chemical response that causes the little creature to quickly burrow into the sand, avoiding what might be a predator. This simple light detection system couldn't tell the worm what was casting the shadow, or how large it was, or whether it was actually dangerous. But it provided enough information to trigger a potentially life-saving response. As these early visual systems continued to evolve, they began to develop more sophisticated capabilities. Some organisms evolved eye spots that could distinguish between different intensities of light, allowing them to navigate toward brighter or darker areas depending on their needs. Others developed the ability to detect the direction from which light was coming, giving them a primitive sense of spatial orientation that helped with navigation and movement. One of the most important evolutionary innovations during this period was the development of shading structures around light-sensitive cells. Some organisms evolved small ridges or depressions that partially blocked light from certain directions, creating the first primitive directional light sensors. These structures worked like the brim of a hat, casting shadows that helped the organism determine not just whether light was present, but which direction it was coming from. Imagine watching one of these early creatures with directional light sensors as it moves through its underwater environment. When light strikes its eye spot from directly above, all the light-sensitive cells are equally illuminated. But when light comes from one side, the shading structure blocks some of the light, creating a pattern of illumination that tells the organism which way to turn a face toward or away from the light source. This simple system provided the foundation for all future developments in spatial vision and navigation. Over millions of years, these shading structures gradually became more elaborate and effective. Natural selection favored organisms with deeper depressions around their light-sensitive cells, because these provided better directional information. Eventually, some of these depressions became so deep that they formed cup-shaped structures, with the light-sensitive cells lining the inner surface of the cup, and the opening pointing outward toward the environment. These cup-shaped proto-eyes represented a major advance in visual capability. The geometry of the cup meant that light could only reach the light-sensitive cells from a relatively narrow range of directions, providing much better directional information than the simple eye spots of earlier organisms. For the first time, primitive creatures could begin to distinguish not just the intensity and direction of light, but could start to detect patterns of light and shadow that corresponded to objects in their environment. Picture the underwater world as seen through one of these early cup-shaped eyes. Not the sharp, detailed vision we take for granted, but a fuzzy awareness of light and shadow patterns that could indicate the presence of food, predators, or obstacles. A large fish swimming nearby might appear as a moving shadow that darkened and brightened different parts of the eye cup as it passed. The edge of a rocky outcrop might create a distinct boundary between lighter and darker regions that could help with navigation. The evolution of these cup eyes set the stage for one of the most remarkable developments in the history of vision: the formation of the first true image-forming eyes. This transition happened when the opening of the eye cup gradually became smaller, creating what is essentially a pinhole camera. The smaller opening meant that light from any particular point in the environment could only reach a specific small area on the light-sensitive surface, creating the first crude but recognizable images. This pinhole camera arrangement represented a revolutionary advance in visual capability. For the first time in Earth's history, living creatures could see actual images of their surroundings, however blurry and imperfect those images might have been. The shadows and light patterns that had been the limit of earlier vision were replaced by the beginnings of true sight, the ability to distinguish shapes, detect movement, and recognize objects in the environment. The transition from simple light detection to image formation happened gradually over millions of years, with each small improvement providing survival advantages that were selected for by evolution. Organisms with slightly smaller eye openings could see slightly sharper images, making them better at avoiding predators or finding food. Those with more light-sensitive cells could see in dimmer conditions or detect more subtle details in their visual field. During this long period of visual evolution, different lineages of organisms began experimenting with different solutions to the challenges of sight. Some developed multiple simple eyes scattered across their bodies, creating a kind of distributed vision system that could detect movement and changes in light from many directions simultaneously. Others concentrated their visual resources into fewer, more sophisticated eyes that could provide better image quality and more detailed information about specific parts of their environment. The diversity of early visual systems that evolved during this period was remarkable. Some organisms developed eyes with hundreds of tiny lenses, each creating its own small image that combined with the others to form a mosaic view of the world. Others evolved large, simple eyes that gathered as much light as possible to see in the dim conditions of deep water or nighttime environments. Still others developed specialized eyes that were particularly sensitive to specific colors of light, allowing them to detect prey or predators that might be invisible to other visual systems. Picture the ancient oceans of 500 million years ago, filled with creatures sporting an amazing variety of experimental eye designs. There were animals with compound eyes made of thousands of individual light-detecting units, others with simple but large cup-shaped eyes, and still others with the first primitive versions of the camera-like eyes that would eventually evolve into human vision. Each of these different visual systems provided its owner with a unique way of perceiving and interacting with the world of light. One of the most successful early eye designs was the compound eye, which consisted of many individual visual units called ommatidia, each containing its own lens and light-sensitive cells. This design provided several advantages. It was excellent at detecting movement, it gave a very wide field of view, and it could be quite sensitive to changes in light intensity. Many of the arthropods that developed compound eyes during this period were so successful that their descendants, including insects and crustaceans, continue to use very similar visual systems today. At the same time, other evolutionary lineages were developing what would eventually become the vertebrate eye, a more centralized visual system with a single large lens that could focus light onto a concentrated area of light-sensitive cells. This design traded off some of the wide field of view and movement detection capabilities of compound eyes for the ability to create sharper, more detailed images of objects in the environment. The evolution of these early image-forming eyes coincided with one of the most important periods in the history of life on Earth, the Cambrian explosion, when complex multicellular animals first appeared in large numbers and great diversity. The development of vision during this period wasn't just a coincidence. The ability to see played a crucial role in driving the rapid evolution of new body forms, behaviors, and ecological relationships that characterized this remarkable time. With the advent of true vision, the arms race between predators and prey intensified dramatically. Predators that could see their prey had enormous advantages, but this created strong selective pressure for prey animals to develop better camouflage, faster escape responses, and their own visual systems for detecting approaching threats. The result was an evolutionary feedback loop that drove rapid improvements in visual capability and the development of increasingly sophisticated eyes. Picture the ancient seafloor during the Cambrian period as vision was transforming the nature of life itself. For the first time, predators could actively hunt by sight rather than relying on chemical cues or random encounters. Prey animals that had previously been safe hiding in plain sight now needed protective shells, spines, or camouflage to avoid being spotted by the new generation of visually guided hunters. The peaceful microbial world of earlier eras gave way to a more dynamic and visually driven ecosystem. The development of vision also enabled new kinds of social behaviors and communication. Animals could now recognize members of their own species by sight, coordinate group activities through visual signals, and engage in complex mating displays that relied on the ability to see colors, patterns, and movements. The visual world became not just a source of information about food and danger, but a medium for social interaction and cultural transmission. As you settle deeper into rest tonight, consider the remarkable journey that led from those first simple light-sensitive molecules in ancient bacteria to the sophisticated visual systems that allow you to see the world around you. Every time you open your eyes and see light, you're experiencing the culmination of billions of years of evolutionary refinement that began with the humblest chemical responses to photons in the primordial seas. The same fundamental processes that created the first eye spots in primitive organisms continue to operate in your own vision today. The photoreceptor molecules in your eyes are distant descendants of those early light-sensitive proteins, refined and perfected through eons of evolutionary improvement, but still performing the same basic function of converting light energy into neural signals that your brain can interpret as sight. In the gentle transition from wakefulness to sleep, your visual system gradually reduces its activity, but it never completely shuts down. Even with your eyes closed, the light-sensitive cells in your retinas continue their patient work, ready to respond instantly if light should appear. This constant vigilance connects you to the very earliest origins of vision, when the ability to detect light was often the difference between life and death for our distant ancestors. The story of vision's evolution reminds us that the most complex and sophisticated systems often grow from the simplest beginnings, through patient accumulation of small improvements over vast periods of time. What began as a simple chemical response to light in primitive bacteria eventually flowered into the rich visual experience that allows you to appreciate sunsets, recognize faces, read these words, and navigate through your complex visual world with unconscious ease. As the evolutionary development of vision continued over millions of years, something truly remarkable began to happen in the eyes of various creatures scattered across Earth's ancient landscapes and seascapes. The simple ability to detect light and form basic images was gradually joined by an even more sophisticated capability: the power to distinguish between different wavelengths of electromagnetic radiation to perceive what we have come to know as color. This development would transform not only how animals experience their world, but would eventually reshape the very appearance of life on Earth itself, creating a feedback loop between vision and beauty that continues to this day. To understand how color vision emerged, picture the light that bathes our world as something far richer and more complex than it might first appear. What we experience as simple white sunlight is actually a mixture of electromagnetic radiation spanning a vast range of wavelengths, from the short, energetic waves we call violet and blue, through the medium wavelengths of green and yellow, to the longer, gentler waves of red and infrared. Each of these different wavelengths carries its own signature, its own unique way of interacting with matter, its own potential for conveying information about the world. The earliest light-sensitive organisms could detect the presence or absence of this radiation, but they experienced it as an undifferentiated whole, like listening to a symphony but being unable to distinguish between the different instruments playing together. The evolutionary development of color vision was like gradually gaining the ability to hear individual notes within that cosmic symphony of light, to perceive the subtle differences between wavelengths that had always been there, but had remained invisible to previous generations of living creatures. The first steps toward color vision began with simple chemical differences in the light-sensitive molecules that line primitive eyes. Just as different materials in your everyday world appear different colors because they absorb and reflect different wavelengths of light, the protein molecules responsible for detecting light in early organisms occasionally underwent genetic changes that altered their sensitivity to specific parts of the light spectrum. A random mutation might create a photoreceptor protein that responded most strongly to shorter wavelengths, while another might be most sensitive to longer wavelengths. Picture one of these early organisms, perhaps a small marine creature drifting in the warm shallows of an ancient sea, suddenly blessed with two different types of light-sensitive cells in its simple eyes. For the first time in its lineage's history, this creature could distinguish between the blue-green light filtering down from the surface and the redder light that predominated in deeper waters. This wasn't color vision as we understand it today. There was no conscious perception of blue or red, but it represented the first biological ability to extract different information from different wavelengths of light. This primitive color discrimination provided immediate survival advantages. An organism that could distinguish between the wavelengths of light coming from above and those coming from below had a better sense of orientation in the water column. One that could detect the subtle color differences between various types of food particles could forage more efficiently. Another that could perceive the wavelength patterns reflected by potential predators could avoid danger more effectively. As millions of years passed, natural selection continued to refine and expand these early color vision capabilities. Organisms that developed 3 different types of color-sensitive cells could make even finer distinctions between different wavelengths, creating what we might recognize as the beginning of true color perception. Those with 4 or more types of color receptors could see patterns and contrasts that remained invisible to their competitors, gaining access to hidden layers of visual information that permeated their environment. The development of color vision wasn't uniform across all forms of life. Different evolutionary lineages experimented with different approaches to color detection, creating a remarkable diversity of color vision systems that continues to characterize life on Earth today. Some creatures evolved eyes that were particularly sensitive to the blue and ultraviolet wavelengths that predominate underwater, while others developed vision systems optimized for the red and infrared radiation that filters through forest canopies. Still others created eyes capable of detecting polarized light patterns that remain completely invisible to most other organisms. Picture the ancient world as it might have appeared to some of these early color vision pioneers. The ocean that had seemed like a uniform blue-green environment to earlier generations of marine life suddenly revealed hidden patterns of color and contrast. Patches of plankton became visible as subtle color variations against the water background. The bodies of other creatures showed complex patterns of wavelength reflection that could indicate species, health, emotional state, or reproductive readiness. The simple world of light and shadow that had characterized earlier vision gave way to a rich tapestry of chromatic information. On land, the development of color vision coincided with the evolution of increasingly complex plant communities that were beginning to experiment with their own relationships to light and color. Early plants had been primarily green, using chlorophyll to capture the abundant yellow and red wavelengths of sunlight for photosynthesis. But as animals with color vision became more common, plants began to discover that they could manipulate animal behavior by displaying specific colors in their flowers, fruits, and other structures. This marked the beginning of one of the most beautiful partnerships in the history of life: the coevolution of color vision in animals and color displays in plants. Plants that produced brightly colored flowers found that they could attract insects and other creatures to visit them, facilitating pollination and reproduction. Animals with color vision could easily locate these colorful food sources and distinguish between ripe and unripe fruits. Both partners benefited from this arrangement, and both were driven to develop increasingly sophisticated color capabilities. Imagine walking through one of these early flowering landscapes, seeing it through eyes that were just beginning to develop the capacity for color discrimination. The flowers that appeared as brilliant red or orange to emerging color vision systems weren't necessarily beautiful in any aesthetic sense we would recognize. They were simply biological advertisements, chemical signals translated into visual form, announcing the presence of nectar, pollen, or other resources that animals sought. Over time, however, something remarkable happened to this practical system of color communication. As color vision became more sophisticated and widespread, the range of colors displayed by living things expanded far beyond what was strictly necessary for basic survival functions. Flowers began to appear in subtle shades and complex patterns that seemed to serve no obvious biological purpose. Animal color displays became more elaborate and varied, incorporating hues and combinations that went beyond simple species recognition or health indicators. This explosion of biological color represented the emergence of something that might be called aesthetic evolution, the development of beauty for its own sake, driven by the interactions between increasingly sophisticated color vision systems and the living things they observed. Animals began to show preferences for certain color combinations, certain patterns, certain visual harmonies that had no direct relationship to survival needs, but somehow appealed to their developing visual sensibilities. Picture a world where color was gradually becoming more than just information, where it was beginning to become a source of pleasure, attraction, and aesthetic experience. The harsh, practical world of early evolution was softening into something more complex and beautiful, as the development of color vision created new pressures for visual appeal that went beyond mere survival. This was the beginning of beauty as a biological force, a driver of evolution that would eventually lead to some of the most spectacular visual displays in the natural world. The evolution of color vision also began to influence the development of more sophisticated neural processing systems in the animals that possessed it. Distinguishing between different wavelengths of light required more complex brain circuitry than simple light detection, and animals with better color vision needed more sophisticated visual processing capabilities to make sense of the rich chromatic information their eyes were collecting. This neural complexity, in turn, enabled even more advanced visual capabilities. Animals could begin to recognize complex color patterns, remember the chromatic signatures of important objects in their environment, and make subtle distinctions between similar-looking items based on small differences in their color properties. The simple automatic responses that had characterized earlier vision gave way to more flexible, learning-based visual behaviors that could adapt to changing circumstances and new challenges. As color vision continued to evolve and spread throughout various animal lineages, it began to influence not just individual survival and reproduction, but the very structure of ecological communities. Animals with sophisticated color vision could detect prey or predators that remained invisible to colorblind species, creating new predator-prey relationships and competitive dynamics. Plants that could produce colors visible to some animals, but not others, could selectively attract their preferred pollinators while avoiding others. The underwater world, in particular, became a showcase for the evolutionary potential of color vision and color display. Fish began to evolve brilliant color patterns that serve purposes ranging from camouflage and species recognition to territorial displays and mating signals. Coral reefs became vast, living galleries of biological art, with thousands of species displaying every conceivable combination of colors and patterns in their competition for resources, mates, and territory. Picture these ancient reefs as they might have appeared to a time traveler with modern color vision. Vast, three-dimensional tapestries of living color, where every surface was occupied by creatures displaying their own unique chromatic signatures. The evolution of color vision had transformed what had once been a relatively monochrome underwater world into a kaleidoscope of biological diversity and visual complexity. The development of color vision in flying animals, insects, and eventually birds opened up entirely new possibilities for color communication and display. Three-dimensional movement through the air allowed for dynamic color displays that changed with viewing angle, movement, and lighting conditions. Wings became canvases for iridescent patterns that could flash and shimmer as their owners moved through the air, creating visual signals that were both beautiful and informationally rich. On land, the evolution of color vision in mammals created new opportunities for color-based communication and behavior. Though many mammals have more limited color vision than birds or some insects, they develop their own sophisticated systems for using color information in social interactions, territory marking, and mate selection. The development of color vision in primates, in particular, would eventually lead to some of the most sophisticated color perception systems in the animal kingdom. As millions of years passed, the interaction between evolving color vision and evolving color displays created an accelerating cycle of visual innovation. Each improvement in an animal's ability to see color created opportunities for other organisms to develop new and more sophisticated color signals. These new signals, in turn, created selective pressure for even better color vision systems that could detect and interpret them. This evolutionary arms race of color perception and color display wasn't limited to interactions between different species. It also drove the development of increasingly elaborate color patterns within species, particularly in the context of sexual selection. Animals began to develop color displays specifically designed to attract mates, leading to some of the most spectacular and seemingly impractical color patterns in the natural world. Picture the peacock's tail as an example of this process, taken to an extreme, a massive display of iridescent color and pattern that serves no survival function and actually makes its owner more vulnerable to predators, but has evolved because peahens with sophisticated color vision consistently choose to mate with males displaying the most impressive chromatic presentations. This represents color vision and color display coevolution at its most refined, where aesthetic preferences have become powerful evolutionary forces in their own right. The story of color vision's evolution also reveals something profound about the nature of color itself. The colors that we see and that other animals see don't exist independently in the external world. They are created by the interaction between electromagnetic radiation of different wavelengths and the visual processing systems that detect and interpret them. In a very real sense, color vision didn't just allow animals to detect colors that were already there. It actually created color as a biological and experiential phenomenon. This means that much of the colorful beauty we see in the natural world today exists only because vision systems evolved the capability to perceive it, without eyes to see them. The brilliant red of a cardinal or the deep blue of a mountain lake will be nothing more than different patterns of electromagnetic radiation reflecting off various surfaces. Color vision transformed these physical patterns into the rich, emotional, aesthetically powerful experiences we call color. As you rest here tonight, surrounded by the gentle colors of your own environment, consider that you are experiencing one of the most remarkable achievements in the history of life on Earth. The ability to see color, which we take so completely for granted, represents hundreds of millions of years of evolutionary development and biological innovation. Every color you perceive is the result of incredibly sophisticated molecular and neural machinery working together to extract meaning and beauty from the wavelengths of light that surround us. The colors in your world tonight, the warm glow of artificial lights, the subtle variations in shadow and reflection, even the colors you might see with your eyes closed as random neural activity creates phantom visual experiences. All of these connect you to the vast evolutionary story of vision and color that has been unfolding for hundreds of millions of years. When you close your eyes and drift towards sleep, your color vision systems gradually quiet their activity, but they remain ready to spring back to life at the first sign of light. In your dreams, your brain may continue to generate color experiences, creating visual narratives that draw on the same neural pathways that evolved to process real color information from the external world. Even in sleep, you remain connected to the great story of color vision that transformed our planet from a world of simple light and shadow into the rich, chromatic paradise we experience today. While the evolution of vision was transforming how life perceived the world, an even more fundamental revolution was quietly taking place in the microscopic realm of single-celled organisms floating in Earth's ancient oceans. This transformation would not only change the very air we breathe, but would set the stage for all complex life that followed. It began with the elegant simplicity of photosynthesis, the process by which living things learn to capture sunlight and use its energy to build the molecules of life itself, releasing oxygen as a byproduct that would eventually transform our entire planet. Picture the Earth as it existed roughly 3 billion years ago, when this remarkable process was just beginning to emerge. The atmosphere was radically different from the one you breathe today. It contained virtually no free oxygen, but was instead dominated by gases like methane, ammonia, and carbon dioxide that would be toxic to most modern life forms. The oceans were tinted with iron compounds that gave them a greenish hue, and the sky above was likely a pale orange or pink rather than the familiar blue we know today. Yet in this alien world, the foundations were being laid for one of the most important innovations in the history of life. The earliest photosynthetic organisms were cyanobacteria, tiny, single-celled creatures that developed the remarkable ability to harness the energy in sunlight and use it to convert carbon dioxide and water into the organic compounds they needed for growth and reproduction. This process wasn't invented overnight. It evolved gradually through countless small genetic changes and molecular innovations, each one building upon the previous to create increasingly efficient light harvesting systems. Imagine these early cyanobacteria as nature's first solar panels, microscopic living machines that could capture photons streaming down from the sun and transform their energy into chemical bonds that could be stored and used later. The process they developed was incredibly sophisticated, involving a complex sequence of molecular interactions that modern scientists are still working to fully understand. At its heart was a special type of chlorophyll molecule that could absorb light energy and use it to split water molecules, releasing hydrogen atoms that could be combined with carbon dioxide to create sugars. The byproduct of this water-splitting reaction was oxygen, a highly reactive gas that, in large quantities, would prove toxic to many of the organisms that shared the early Earth environment. But these early photosynthetic bacteria had evolved in a world where oxygen was scarce, so the small amounts they produced initially caused no problems. They simply released this oxygen gas into the surrounding water, where it quickly reacted with dissolved iron and other chemicals, forming compounds that settled to the ocean floor. For millions of years, this process continued quietly and gradually. Populations of cyanobacteria spread throughout the world's oceans, forming vast floating mats and colonies that covered enormous areas of the ocean surface. Each tiny cell was like a miniature factory, constantly absorbing sunlight and carbon dioxide, converting them into organic matter and releasing oxygen as waste. The scale of this operation was almost impossible to imagine. Trillions upon trillions of microscopic organisms working day after day, year after year, gradually altering the chemical composition of the entire planet. Picture the ancient oceans during this period as vast biological workshops where the chemistry of life was being perfected. The water was filled with these microscopic photosynthetic organisms, each one too small to see individually, but collectively forming a green tinge that could be observed from space if there had been anyone there to observe it. During daylight hours, when the sun's energy was available, these bacterial communities would be busily converting carbon dioxide into organic matter, while at night they would rest and consume some of their stored chemical energy for maintenance and growth. The oxygen being produced by this ancient photosynthesis didn't immediately accumulate in the atmosphere because there were so many chemical compounds in the early Earth environment that were eager to react with it. Iron dissolved in seawater readily combined with oxygen to form iron oxides that precipitated out as distinctive red and orange bands in the seafloor sediments. Organic compounds and gases like methane also reacted quickly with any free oxygen, preventing it from building up to significant concentrations. But gradually, over hundreds of millions of years, something remarkable began to happen. The oxygen-consuming chemicals in the oceans and atmosphere became saturated. There simply wasn't enough of them left to react with all the oxygen being produced by the ever-expanding populations of photosynthetic bacteria. For the first time in Earth's history, free oxygen began to accumulate in significant quantities in the atmosphere, marking the beginning of what scientists call the Great Oxidation Event. This transformation wasn't sudden or dramatic in the way we might imagine such a planetary change. It unfolded over hundreds of millions of years, with oxygen levels rising gradually and unevenly as the balance between oxygen production and consumption slowly shifted. There were probably periods when oxygen levels rose more quickly, followed by times when they plateaued or even declined slightly as geological or biological processes temporarily increased oxygen consumption. Picture this gradual oxygenation as similar to filling a vast swimming pool with a garden hose. The water level rises so slowly that you might not notice the change from day to day, but over months and years the transformation becomes undeniable. Similarly, the oxygen content of Earth's atmosphere rose from virtually zero to substantial levels over geological timescales that dwarf human experience. But the cumulative effect was one of the most profound changes in our planet's history. As oxygen levels continued to rise, life on Earth faced a crisis that would reshape the entire biosphere. Many of the organisms that had evolved in the low-oxygen environment of early Earth found the increasingly oxygen-rich atmosphere to be toxic. Oxygen is a highly reactive chemical that can damage cellular structures and interfere with metabolic processes that evolved to function in its absence. For many species, the rising oxygen levels represented an existential threat that would drive them to extinction or force them to adapt to radically new conditions. This period, sometimes called the oxygen catastrophe, saw the extinction of many species that could not cope with the changing atmospheric chemistry. Yet it also created new opportunities for organisms that could not only tolerate oxygen, but actually use it to their advantage. Some bacteria evolved sophisticated cellular machinery that could neutralize the toxic effects of oxygen, while others went even further and learned to use oxygen as a tool for more efficient energy metabolism. The development of oxygen-based metabolism represented another revolutionary innovation in the history of life. Organisms that could use oxygen to help break down organic compounds could extract far more energy from their food than those relying on older, anaerobic metabolic pathways. This gave them significant advantages in growth, reproduction, and competition for resources, driving the evolution of increasingly sophisticated oxygen-using life forms. Imagine the early Earth during this period of atmospheric transformation as a world caught between two different biochemical paradigms. In some environments, deep ocean sediments, hot springs, and other oxygen-poor habitats, the old anaerobic way of life continued much as it had for billions of years. But in the surface waters, and eventually on land, a new oxygen-based ecosystem was emerging, populated by organisms that could harness both the energy of sunlight through photosynthesis and the chemical energy available through oxygen respiration. The rising oxygen levels also had profound effects on Earth's geology and climate. Oxygen reacted with methane in the atmosphere, converting this potent greenhouse gas into carbon dioxide and water vapor. Since methane is much more effective at trapping heat than carbon dioxide, this chemical transformation led to a significant cooling of the global climate. Some scientists believe this cooling was so severe that it triggered a series of ice ages that may have covered the entire planet in ice for millions of years. These dramatic climate changes created additional challenges for life, but they also drove further evolutionary innovation. Organisms that could survive in the harsh conditions of a frozen, oxygen-rich world had to develop new strategies for coping with temperature extremes, seasonal variations in light availability, and the chemical challenges of living in an oxidizing environment. As the Earth gradually warmed again and oxygen levels stabilized at higher concentrations, the stage was set for the next great phase in the evolution of life. The abundant oxygen in the atmosphere made possible the development of complex multicellular organisms with sophisticated metabolic systems that could support larger body sizes and more active lifestyles. The energy efficiency of oxygen-based metabolism provided the foundation for the evolution of animals, with their high energy demands for movement, sensory processing, and complex behaviors. Picture the world as it might have appeared during this crucial transition period, perhaps 2 billion years ago. The oceans were no longer the greenish or reddish color of earlier eras, but were beginning to take on the blue tint we associate with modern seawater. The sky was gradually shifting from its earlier orange or pink hues toward the familiar blue color created by the interaction of sunlight with oxygen and nitrogen molecules in the atmosphere. The iron-rich bands that had characterized earlier seafloor sediments were giving way to new types of rock formations that reflected the chemistry of an oxygen-rich world. The photosynthetic organisms responsible for this transformation continued to evolve and diversify, developing more efficient light harvesting systems and spreading into new environments around the globe. Some evolved into the ancestors of modern plants, eventually developing the complex cellular structures and specialized tissues that would allow them to colonize dry land. Others remained in the oceans, where they continue today as the phytoplankton that form the base of marine food webs and still produce a significant portion of the oxygen we breathe. The process of photosynthesis itself also continued to evolve, becoming more sophisticated and efficient over millions of years. Different lineages of photosynthetic organisms developed slightly different approaches to capturing and using light energy, leading to the diversity of photosynthetic pathways we observe in modern plants and bacteria. Some became specialized for low-light conditions in deep water or forest understories, while others adapted to intense sunlight in desert or high-altitude environments. As oxygen levels approached modern concentrations, they enabled the evolution of increasingly complex ecosystems where photosynthetic organisms formed the foundation of intricate food webs. Primary producers used sunlight to create organic matter from simple inorganic compounds, while consumers at various levels used oxygen respiration to efficiently extract energy from this biological material. The combination of photosynthesis and oxygen respiration created a powerful biological engine that could support far more complex and energy-intensive forms of life than had ever existed before. The atmospheric transformation brought about by photosynthesis also created the conditions necessary for the formation of the ozone layer, a crucial protective shield that filters out harmful ultraviolet radiation from the sun. Without this protection, complex life would have remained confined to deep water or other UV-protected environments. But with the ozone layer in place, organisms could safely venture into shallow waters and eventually onto land, opening up vast new territories for biological exploration and evolution. Picture the ancient Earth during the final stages of this great atmospheric transformation, as oxygen levels approach their modern values and the chemical and physical conditions that characterize our world today were finally established. The blue sky that you see above you, the oxygen you breathe with every breath, the protective ozone layer that shields you from harmful radiation, all of these features of our modern environment are the direct result of billions of years of photosynthetic activity by countless microscopic organisms. The story of how photosynthesis transformed Earth's atmosphere reminds us that some of the most profound changes in our planet's history have come not from dramatic catastrophes or sudden events, but from the patient, persistent work of living things pursuing their daily survival activities. Each tiny cyanobacterium that ever lived contributed its small part to the great project of atmospheric transformation, and their collective effort over geological timescales literally created the world we inhabit today. As you breathe in the oxygen-rich air around you tonight, consider that you are directly benefiting from this ancient biological innovation that began billions of years ago in the microscopic realm of single-celled organisms. Every breath you take connects you to the vast community of photosynthetic organisms that continue their work today, from the trees outside your window to the phytoplankton floating in distant oceans, all of them carrying forward the great project of capturing sunlight and converting it into the chemical energy that powers the living world. The gentle rhythm of your breathing as you settle into rest echoes the ancient rhythm of photosynthesis that has been sustaining life on Earth for billions of years. The daily cycle of capturing light energy during the day and using stored chemical energy at night. The seasonal patterns of growth and dormancy. The long-term cycles of atmospheric change that have shaped our planet's history. In your peaceful rest tonight, you participate in the same fundamental life processes that transformed our world and made all complex life possible. With Earth's atmosphere now rich in oxygen and protected by a developing ozone layer, the stage was set for one of the most spectacular chapters in the story of life. The emergence of complex organisms that could harness light energy not just for survival, but for the creation of elaborate living structures that would transform entire landscapes and seascapes. This period marked the beginning of what we might call the Great Illumination, when light-powered life began to build the magnificent biological architecture that characterizes our modern world, from the towering forests that carpet the continents to the vast coral cities that flourish beneath tropical seas. Picture the Earth as it existed roughly 500 million years ago, during the period scientists call the Cambrian, when complex multicellular life was beginning to flourish in the oxygen-rich oceans. The clear blue waters were filled with an abundance of nutrients and bathed in sunlight that could now penetrate deep into the water column without being absorbed by the organic haze that had characterized earlier oceans. In this bright, clean environment, photosynthetic organisms began to experiment with new ways of capturing and using light energy that would eventually give rise to some of the most beautiful and complex ecosystems our planet has ever known. The first great light-powered structures to emerge were the earliest coral reefs, though these ancient reefs were quite different from the tropical paradises we know today. The organisms that built them were not true corals, but rather ancient relatives that had discovered something remarkable. They could form partnerships with tiny photosynthetic algae that would live within their tissues, sharing the light energy they captured through photosynthesis in exchange for protection and nutrients. This symbiotic relationship represented a new form of biological cooperation that would prove to be one of the most successful strategies in the history of life. Imagine descending through the clear waters of an ancient tropical sea to observe one of these early reef communities taking shape. The reef-building organisms appear as small, cup-shaped structures growing on rocky surfaces in the shallow, sunlit waters near shore. Each individual is only a few millimeters across, but they grow in vast colonies that slowly spread across the seafloor, building upon the skeletons of previous generations to create three-dimensional structures that rise toward the surface like underwater cities. Within the tissues of each reef-building organism live millions of microscopic algae, so small that hundreds could fit on the head of a pin. These tiny partners spend their days capturing sunlight and converting carbon dioxide dissolved in seawater into organic compounds that they share with their hosts. In return, the reef builders provide the algae with a safe home, nutrients like nitrogen and phosphorus, and a position in the water column where they can access abundant sunlight for photosynthesis. This partnership proved to be extraordinarily successful because it combined the advantages of both plant and animal lifestyles. The algae provided a constant supply of food energy that allowed the reef builders to grow much faster than they could have survived on captured prey alone, while the animals provided protection from predators and access to nutrients that were often scarce in tropical waters. Together, they could thrive in the bright, nutrient-poor conditions of tropical seas where neither partner could have succeeded on its own. As these early reef communities continued to grow and spread, they began to modify their environment in ways that made it even more suitable for light-based life. The three-dimensional structure of the reefs created countless small habitats with different lighting conditions, from the bright, sun-drenched surfaces to the dim, filtered light of caves and crevices. This diversity of light environments allowed different species of photosynthetic organisms to specialize for particular conditions, creating the remarkable diversity that would eventually characterize coral reef ecosystems. Picture the reef as it might have appeared during its daily cycle of growth and activity. During the daylight hours, when sunlight was abundant, the symbiotic algae within the reef builders would be busy with photosynthesis, producing organic compounds that they shared with their hosts. The reef builders themselves would use this energy to extract calcium carbonate from seawater and deposit it as new skeleton material, gradually adding to the reef structure. The entire community would be bustling with activity as various creatures took advantage of the abundant food and shelter provided by the growing reef. At night, when photosynthesis ceased, the reef would take on a different character. Many of the reef builders would extend their tentacles to capture plankton and small prey from the water column, supplementing the energy they received from their algal partners during the day. Nocturnal creatures would emerge from their daytime, hiding places to forage among the reef structures, while others would retreat into protective crevices to wait for dawn. As millions of years passed, these reef ecosystems continued to evolve and become more complex. New species of reef builders evolved, each with their own particular growth forms and partnerships with different types of algae. Some grew as massive, dome-shaped colonies that could withstand strong wave action in shallow water, while others developed delicate, branching forms that were perfectly adapted to capturing light in deeper, calmer waters. Still others evolved as flat, plate-like structures that could maximize their surface area for light collection while minimizing the energy required for skeleton construction. The success of these light-powered reef communities began to attract other organisms that wanted to take advantage of the abundant food and shelter they provided. Fish evolved that were specifically adapted to reef environments, with specialized feeding behaviors that allowed them to harvest algae, capture small prey among the reef structures, or even feed directly on the reef builders themselves. Many of these fish developed cleaning relationships with the reef organisms, removing parasites and dead tissue in exchange for food and protection. Meanwhile, on the land surfaces that were beginning to emerge as continents drifted and collided, another revolution in light-powered life was taking place. Early plants, descendants of green algae that had learned to live in freshwater environments, were beginning to experiment with life outside the water entirely. This transition to terrestrial life required solving numerous challenges related to water conservation, structural support, and reproduction, but it opened up vast new territories for photosynthetic colonization. The first land plants were small, simple organisms that hugged the ground in moist environments near water sources. They had no true roots, stems, or leaves, but rather grew as loam mats of green tissue that could absorb water and nutrients directly from their surroundings. These humble pioneers began the process of soil formation as their remains accumulated and decomposed, creating the foundation for more complex plant communities that would follow. Picture these early terrestrial landscapes as vast expanses of bare rock and sediment punctuated by small patches of green where primitive plants had managed to establish themselves. The contrast between the living and non-living areas would have been stark, with the photosynthetic organisms creating islands of biological activity in an otherwise largely sterile environment. Yet even these simple plant communities began to modify their surroundings in important ways. creating microenvironments with different temperature, humidity, and nutrient conditions that would eventually support more diverse forms of life. As plants continued to evolve and adapt to terrestrial conditions, they developed increasingly sophisticated structures for capturing light and competing with their neighbors for access to this precious resource. Some evolved taller growth forms that could overshadow their competitors, while others developed more efficient light-capturing systems that allowed them to prosper in the shade of larger plants. The evolution of true roots allowed plants to access water and nutrients from deeper soil layers, while the development of specialized conducting tissues enabled them to grow to larger sizes without losing the ability to transport water and nutrients throughout their bodies. The emergence of trees marked a particularly important milestone in the terrestrial illumination story. These tall, woody plants could capture light from high above the ground, while creating complex, three-dimensional habitats that supported diverse communities of other organisms. The first forests began to appear as trees learned to grow together in communities where different species specialized for different light conditions, creating layered canopies that efficiently captured nearly all the sunlight falling on the forest ecosystem. Imagine walking through one of these early forests as they began to develop their characteristic structure and diversity. The forest floor would be relatively dim, illuminated only by the filtered sunlight that managed to penetrate through the developing canopy above. Here, shade-tolerant plants would specialize in capturing and using the limited light available, often developing large, broad leaves that could maximize their light-collecting surface area. Higher up, at various levels in the canopy, different species would compete for access to brighter conditions, creating a complex, three-dimensional mosaic of light and shadow. The development of forests had profound effects on Earth's climate and atmospheric composition. The vast leaf surfaces of forest trees became enormous photosynthetic factories that removed carbon dioxide from the atmosphere and converted it into wood, leaves, and other organic materials. This biological carbon sequestration helped to moderate Earth's climate while providing the foundation for complex food webs that could support diverse communities of animals, fungi, and microorganisms. Forest ecosystems also began to modify local weather patterns through their effects on temperature and humidity. The shade provided by forest canopies cooled surface temperatures during hot days, while the transpiration of water from leaves increased local humidity and contributed to cloud formation and precipitation. These effects created positive feedback loops that helped forests expand their range and create the conditions necessary for their own continued growth and development. As both marine and terrestrial light-powered ecosystems continued to evolve and expand, they began to influence each other in important ways. Forests along coastlines provided nutrients that washed into the ocean and supported marine productivity, while ocean currents influenced by the shape of continents affected the climate conditions that determined where different types of forests could grow. The global carbon cycle became increasingly complex as carbon moved between the atmosphere, oceans, and terrestrial ecosystems through the activities of photosynthetic organisms. The Great Illumination also marked the beginning of more complex interactions between light-powered primary producers and the consumers that depended on them. Herbivorous animals evolved sophisticated strategies for harvesting the energy stored in plant tissues, while plants developed defensive compounds and structures to protect themselves from being consumed. These evolutionary arms races led to increasing diversity and specialization in both plant and animal communities. Picture the Earth during the height of this Great Illumination period, perhaps 400 million years ago, when both marine and terrestrial light-powered ecosystems had reached new levels of complexity and productivity. Vast coral reefs stretched across tropical shallow seas, creating underwater rainforests that supported incredible diversity of marine life. On land, extensive forests covered much of the available terrain, their green canopies visible from space as they converted sunlight into the biological energy that powered increasingly complex terrestrial ecosystems. The success of these light-powered ecosystems also created new opportunities for organisms that could specialize in consuming the abundant plant and algal material they produced. The first large herbivorous animals evolved during this period, taking advantage of the vast quantities of photosynthetic tissue that had become available in both marine and terrestrial environments. These primary consumers, in turn, supported the evolution of carnivorous animals that could feed on the herbivores, creating the complex food webs that characterize modern ecosystems. The Great Illumination period also saw the evolution of more sophisticated relationships between plants and animals, including some of the first examples of pollination mutualisms where animals help plants reproduce in exchange for food rewards. These partnerships represented a new form of cooperation between organisms that had originally evolved quite independently, demonstrating how light-powered ecosystems could foster innovation and collaboration across different kingdoms of life. As the day-night cycle continued to drive the rhythms of photosynthesis and respiration in these expanding light-powered ecosystems, the global patterns of oxygen and carbon dioxide concentration began to fluctuate on both daily and seasonal timescales. During the day, when photosynthesis was active, oxygen levels would rise slightly, while carbon dioxide concentrations decreased. At night, when respiration dominated, the pattern would reverse. These daily fluctuations became more pronounced as light-powered ecosystems expanded and became more productive. The seasonal patterns were even more dramatic, particularly in regions where plant growth was strongly seasonal due to temperature or rainfall patterns. During growing seasons, when plants were actively photosynthesizing and producing new tissue, atmospheric carbon dioxide levels would drop while oxygen concentrations increased. During dormant seasons, when many plants had stopped growing but decomposition continued, the pattern would reverse. These seasonal oscillations in atmospheric composition became one of the signatures of a planet where light-powered life had become a dominant force in global biogeochemical cycles. The Great Illumination also marked the beginning of more complex landscape-scale patterns in the distribution of light-powered ecosystems. Different types of forests began to specialize for different climate conditions, creating the biome patterns that still characterize terrestrial ecosystems today. Tropical forests developed in regions with abundant year-round sunlight and moisture, while temperate and boreal forests evolved to take advantage of seasonal variations in light and temperature. Grasslands emerged in regions where fire, grazing, or drought prevented forest establishment, but where enough light and moisture were available to support herbaceous photosynthetic communities. Similarly, in marine environments, different types of light-powered ecosystems began to specialize for different water depths, temperatures, and nutrient conditions. Coral reefs flourished in warm, clear, nutrient-poor tropical waters, where their symbiotic partnerships gave them advantages over other types of communities. Kelp forests evolved in cooler, nutrient-rich waters where large brown algae could grow to enormous sizes and create complex, three-dimensional habitats. Open ocean communities developed strategies for life in the vast expanses of clear blue water where nutrients were scarce but light was abundant. As you rest here tonight, consider that you are surrounded by the legacy of this great illumination that began hundreds of millions of years ago. The oxygen you breathe was produced by countless generations of photosynthetic organisms working together to capture sunlight and convert it into the chemical energy that powers life on Earth. The complex ecosystems that characterize our modern world, from the tropical rainforests to the coral reefs, are all descendants of the light-powered communities that first learned to harness the sun's energy for building elaborate biological structures. The forests outside your window, the parks in your city, even the small plants growing in indoor spaces, all carry forward the ancient tradition of capturing light and converting it into living tissue that supports the intricate web of relationships we call ecology. In your peaceful rest tonight, you participate in the same fundamental cycles of energy capture and storage that have sustained complex life on Earth for hundreds of millions of years, connecting you to the grand story of how light built the illuminated world we inhabit today. As the Earth's landscapes and seascapes filled with the complex light-powered ecosystems of the Great Illumination, The animals that inhabited these environments faced new challenges and opportunities that would drive the evolution of increasingly sophisticated vision systems. The abundance of light-based life created rich visual environments filled with patterns, colors, and movements that could provide crucial information about food, predators, mates, and navigation routes. In response, natural selection began crafting some of the most remarkable and specialized visual systems ever to evolve, turning various creatures into true masters of light detection and interpretation. Picture the ancient oceans during this period of visual innovation, now teeming with complex coral reef communities and diverse marine life that created underwater landscapes of extraordinary visual richness. In these bright, clear waters, predators and prey engaged in evolutionary arms races that drove rapid improvements in visual acuity, color discrimination, and motion detection. The simple eye spots and cup-shaped eyes of earlier eras gave way to sophisticated optical systems that could rival or even surpass modern camera technology in their precision and capability. One of the most remarkable developments during this period was the evolution of compound eyes in arthropods, the group that includes insects, crustaceans, and their relatives. These extraordinary visual systems consisted of hundreds or even thousands of individual optical units called ommatidia, each containing its own lens, light-sensitive cells, and neural processing circuits. Rather than forming a single large image like human eyes do, compound eyes created a mosaic of small images that could be processed together to provide incredibly detailed information about movement, color patterns, and spatial relationships. Imagine looking through a compound eye as you observe the underwater world of an ancient coral reef. Instead of seeing a single, unified view of your surroundings, you would experience a pixelated panorama made up of thousands of individual image points, each providing its own piece of visual information. This might seem like a disadvantage compared to the sharp, continuous images formed by camera-like eyes, but compound vision offered unique benefits that made it extraordinarily successful in many environments. The most remarkable advantage of compound eyes was their ability to detect movement with incredible precision and speed. Because each ommatidium was oriented in a slightly different direction, any moving object would create a characteristic pattern of changing illumination across the eye surface that could be instantly recognized and tracked. This made compound-eyed animals supremely effective at detecting approaching predators, pursuing prey, or following potential mates through complex, three-dimensional environments. The mathematical precision of compound eye design was truly extraordinary. The angles between adjacent ommatidia were carefully optimized to provide the best possible resolution while maximizing sensitivity to light and movement. The neural processing systems that interpreted signals from thousands of individual optical units had to solve complex computational problems in real time, extracting meaningful patterns from vast amounts of visual data flowing in parallel streams from across the eye surface. As compound eyes continued to evolve, different species developed specialized versions adapted for their particular lifestyles and environments. Some aquatic arthropods evolved compound eyes with thousands of large ommatidia that could gather maximum light in the dim conditions of deeper water. Others developed eyes with smaller, more numerous optical units that provided extremely fine resolution for detecting small prey or navigating through complex reef structures. Still others evolved compound eyes that were particularly sensitive to specific colors or polarization patterns that were important for their survival strategies. Picture a mantis shrimp prowling through a coral reef environment, armed with perhaps the most sophisticated compound eyes ever evolved. These remarkable predators possess compound eyes with up to 16 different types of color-sensitive cells, compared to the 3 types found in typical human vision. This allows them to see colors and patterns that remain completely invisible to most other animals, including complex polarization patterns that they use for communication and navigation. The mantis shrimp's eyes can move independently of each other, allowing the animal to scan its environment for threats and opportunities while maintaining visual contact with specific targets. Each eye contains specialized regions optimized for different visual tasks. Some areas are best for detecting movement, others for color discrimination, and still others for perceiving fine details. The neural processing required to integrate all this visual information represents one of the most sophisticated biological computing systems ever evolved. While arthropods were perfecting compound vision, other evolutionary lineages were developing equally impressive but fundamentally different approaches to mastering light. Fish, in particular, evolved remarkable adaptations for vision in aquatic environments where light behaves very differently than it does in air. Water absorbs and scatters light in wavelength-specific ways, creating unique challenges and opportunities for visual system design. Many fish evolved eyes that could adjust their sensitivity across wide ranges of light conditions, from the bright surface waters to the perpetual twilight of deeper zones. Some developed specialized retinas with multiple layers of light-sensitive cells that could capture photons at different depths within the eye, maximizing light-gathering efficiency in dim conditions. Others evolved sophisticated lens systems that could change shape to maintain focus across wide ranges of distances, allowing them to spot small prey items close by or large predators far away. The visual challenges of underwater life also drove the evolution of specialized color vision systems in fish. Water preferentially absorbs longer wavelengths of light, so red colors that appear vivid near the surface become increasingly dim and eventually disappear entirely in deeper water. Different fish species evolve color vision systems optimized for their particular depth ranges, with some developing enhanced sensitivity to the blue and green wavelengths that penetrate deepest into water, while others retain broad-spectrum color vision for life in shallow, full-spectrum environments. Picture a school of fish moving through the dappled light of a shallow coral reef, their sophisticated visual systems constantly processing information about the changing patterns of light and shadow created by sunlight filtering through moving water. Each fish must simultaneously track the movements of its neighbors to maintain school cohesion, watch for predators that might be stalking the group, and search for food items that could provide their next meal. The visual processing required for these multiple simultaneous tasks represents a remarkable achievement in biological engineering. Some fish evolved even more specialized visual adaptations for particular lifestyles. Deep-sea fish developed enormous eyes with incredibly sensitive retinas that could detect the faintest glimmers of bioluminescent light in the eternal darkness of the ocean depths. Others evolved tubular eyes that could be aimed upward to spot the silhouettes of prey against the faint downwelling light from the surface. Still, others developed eyes with specialized yellow lenses that could filter out blue light and enhance their ability to see the red bioluminescence they use for communication. The evolution of sophisticated vision in fish also drove the development of equally remarkable visual adaptations in their predators and prey. Octopuses and other cephalopods evolved camera-like eyes that rivaled those of vertebrates in their optical precision, despite having evolved completely independently. These marine predators developed extraordinary abilities to change their skin color and pattern in response to what they saw, creating some of the most sophisticated camouflage systems in the natural world. Meanwhile, in terrestrial environments, the transition to life on land created new opportunities and challenges for visual system evolution. Air is much more transparent to light than water, allowing for much greater visual ranges and more complex optical effects. The abundance of plant life created visually rich environments filled with green foliage, colorful flowers, and complex patterns of light and shadow that provided both opportunities and challenges for animal vision systems. Birds, as they evolved from their dinosaur ancestors, developed some of the most remarkable visual systems ever created by evolution. Many birds possess color vision that extends well into the ultraviolet range, allowing them to see patterns and markings on flowers, fruits, and other birds that remain completely invisible to mammals. Their retinas contain specialized oil droplets that act as color filters, enhancing color discrimination and reducing glare from bright sunlight. The visual acuity of many birds far exceeds that of humans, allowing them to spot small prey items or potential threats from enormous distances. Eagles and other raptors evolved eyes so large relative to their body size that they had to develop specialized skull structures to accommodate them. The density of light-sensitive cells in raptor retinas can be several times higher than in human eyes, providing resolution that allows them to spot mouse-sized prey from heights of several hundred meters. Picture a hawk soaring high above an ancient forest, its extraordinary visual system scanning the landscape below for signs of movement that might indicate prey. The bird's eyes can simultaneously focus on objects at different distances, track multiple potential targets, and maintain awareness of its own flight path and nearby obstacles. The neural processing required to integrate all this visual information while controlling complex flight maneuvers represents one of the most sophisticated real-time computing systems in the biological world. As mammals began to diversify and colonize various terrestrial environments, they too developed specialized visual adaptations, though often with different emphases than those seen in birds. Many mammals evolved enhanced night vision capabilities that allowed them to be active during periods when their competitors or predators were less visually capable. This required sophisticated adaptations, including enlarged eyes, specialized retinal structures that could amplify weak light signals, and neural processing systems that could extract meaningful information from noisy, low-light visual input. Some mammals developed particularly sophisticated adaptations for specific visual environments. Cats evolved eyes with highly reflective layers behind their retinas that gave them a second chance to capture photons that might otherwise escape, creating the characteristic eye shine that makes their eyes glow in the dark. Many ungulates developed eyes positioned on the sides of their heads to provide wide fields of view for detecting predators, while their predators evolved forward-facing eyes that provided the stereoscopic depth perception necessary for accurately judging distances when pursuing prey. The evolution of sophisticated mammalian vision also coincided with the development of complex social behaviors that relied heavily on visual communication. Many mammals evolved elaborate visual displays for courtship, territorial defense, and social coordination that required both the ability to produce complex visual signals and the visual acuity necessary to interpret them accurately. This created feedback loops between visual system evolution and behavioral complexity that drove both to increasing levels of sophistication. In nocturnal environments, some mammals developed alternative strategies for gathering visual information in low-light conditions. Several lineages independently evolved the ability to see infrared radiation, allowing them to detect the body heat of prey or predators even in complete darkness. Others enhanced their sensitivity to movement and contrast, trading color vision for the ability to detect subtle changes in their visual environment that might indicate approaching threats or opportunities. Picture the Earth during this remarkable period of visual evolution, roughly 200 million years ago, when sophisticated vision systems had become widespread across both marine and terrestrial environments. The oceans were filled with creatures sporting an amazing variety of visual adaptations, from the compound eyes of ancient arthropods to the camera-like eyes of early cephalopods and fish. On land, the first mammals and birds were experimenting with visual systems that would eventually give rise to some of the most sophisticated optical equipment ever evolved. The diversity of visual solutions that evolved during this period demonstrates the remarkable creativity of evolutionary processes when faced with the challenge of extracting information from light. Different lineages discovered different ways to solve similar visual problems, leading to convergent evolution of camera-like eyes in vertebrates and cephalopods, compound eyes in various arthropod groups, and specialized visual adaptations in countless other species. The arms races between predators and prey during this period drove particularly rapid evolution of visual capabilities. Predators with better eyesight were more successful at catching prey, which created selective pressure for prey animals to develop better vision for detecting approaching threats, more effective camouflage to avoid visual detection, or faster escape responses when spotted. These feedback loops accelerated the pace of visual evolution and drove the development of increasingly sophisticated optical and neural systems. The evolution of color vision during this period also reached new levels of sophistication, with some animals developing the ability to see combinations of colors that exceed anything achievable by human vision. The variety of color vision systems that evolved reflects the diversity of visual environments and tasks that different animals needed to solve, from detecting ripe fruits against green foliage to distinguishing between different species of flowers or recognizing the subtle color signals used in social communication. As you rest here tonight, your own eyes represent the culmination of hundreds of millions of years of visual evolution. The optical structures that focus light onto your retinas, the photoreceptor cells that convert light into neural signals, and the complex brain circuits that process visual information all carry the legacy of this long history of evolutionary innovation. Even as you close your eyes and prepare for sleep, your visual system remains ready to spring back into action, drawing on ancient capabilities that connect you to the remarkable story of how life learned to master light. The same fundamental principles that guided the evolution of compound eyes in ancient arthropods, the sophisticated color vision of tropical fish, and the extraordinary acuity of soaring birds continue to operate in your own visual experience. Every time you see movement in your peripheral vision, distinguish between different colors, or judge the distance to an object, you're using biological technologies that were refined over geological timescales through the patient work of evolutionary processes that never stop seeking better solutions to the challenges of extracting meaningful information from light. In your dreams tonight, your brain may continue to generate visual experiences that draw on these same ancient pathways, creating images and patterns that reflect the deep connections between your visual system and the fundamental ways that life has learned to interact with light throughout Earth's long history. While living things were evolving ever more sophisticated ways to capture and use light, the photons streaming from our sun were simultaneously sculpting the very face of our planet through their interactions with the atmosphere, oceans, and land surfaces. This ongoing dance between light and matter has painted the landscapes we see today, creating the weather patterns that distribute life-giving water around the globe, carving mountains and valleys through the forces unleashed by solar heating, and establishing the great circulation systems that make Earth a dynamic, ever-changing world where light serves not just as energy for life, but as the master artist shaping the canvas on which that life exists. Picture our planet as seen from space during those ancient times when complex life was first flourishing, a beautiful blue marble suspended in the cosmic darkness, its surface constantly changing as solar energy drives vast atmospheric and oceanic circulation patterns that never rest. The light from our sun doesn't simply illuminate this world. It actively transforms it, moment by moment, through countless subtle interactions that accumulate over time into the geological and climatological forces that have shaped every landscape feature we observe today. The most fundamental way that light shapes our world is through the simple process of heating. As photons from the sun strike Earth's surface, they transfer their energy to whatever material absorbs them, warming the land, the oceans, and the atmosphere in patterns that depend on the angle of incoming sunlight, the reflective properties of different surfaces, and the complex ways that heat moves through air and water. This differential heating creates the temperature gradients that drive all of Earth's weather systems, from the gentlest morning breeze to the most powerful hurricanes. Imagine the Earth during a single day as this solar heating process unfolds across its surface. As dawn breaks across a continent, the first rays of sunlight begin warming the land, which heats up more quickly than nearby bodies of water. This creates temperature differences that cause air to begin moving, rising over the warmer land and creating gentle onshore breezes as cooler air flows in from over the water to replace it. Throughout the day, as the sun climbs higher and its light grows more intense, these temperature differences become more pronounced, driving stronger winds and more complex circulation patterns. The way light interacts with different types of surfaces creates the fundamental patterns that govern our planet's climate systems. Dark surfaces like forests and bare soil absorb most of the sunlight that strikes them, converting it into heat that warms the air above. Light-colored surfaces like snow, ice, and white sand reflect much of the incoming solar energy back to space, remaining relatively cool even under intense sunlight. These differences in heating create the temperature contrasts that drive wind patterns, ocean currents, and the great circulation systems that transport heat and moisture around the globe. Water, which covers most of our planet's surface, has particularly interesting interactions with sunlight that make it central to almost all Earth's climate processes. The clear blue oceans absorb solar energy efficiently, but because water has a high heat capacity, it takes a great deal of energy to warm it significantly. This means that large bodies of water heat up slowly during the day and cool down slowly at night, creating moderating effects on local and regional climate that make coastal areas generally milder and less variable than continental interiors. Picture the vast expanse of an ancient ocean as it responds to the daily cycle of solar heating. During the day, the surface waters warm gradually as they absorb sunlight, but this warmth doesn't immediately penetrate to great depths. Instead, it creates a warm surface layer that may be quite different in temperature from the cooler water below. At night, this surface layer cools by radiating heat back to space, but it loses its heat much more slowly than land surfaces do, creating the thermal stability that makes oceans such powerful climate moderators. The evaporation of water from ocean surfaces represents another crucial way that light energy shapes our world's landscape and weather patterns. As solar energy strikes the ocean surface, it provides the heat needed to convert liquid water into water vapor, which rises into the atmosphere, carrying enormous amounts of energy with it. When this water vapor eventually condenses back into liquid droplets high in the atmosphere, it releases that stored energy, providing the power that drives many of our planet's most dramatic weather phenomena. This solar-powered water cycle creates the precipitation patterns that determine where deserts form and where lush forests can grow, where rivers flow and where lakes accumulate, where glaciers build up and where they retreat. Every raindrop that falls, every snowflake that drifts to Earth, every morning dew that glistens on grass represents solar energy that was captured at the ocean's surface, carried through the atmosphere, and released again as water returns from vapor to liquid form. Imagine following a single molecule of water as it participates in this grand solar-powered cycle. Beginning in a tropical ocean, it absorbs enough energy from sunlight to break free from the liquid surface and rise as invisible vapor into the atmosphere. Carried by winds that are themselves driven by solar heating patterns, it travels perhaps thousands of miles before encountering conditions that cause it to condense into a tiny droplet within a cloud. Eventually, it falls as precipitation onto a distant landscape, where it might flow in rivers back to the sea, soak into soil to nourish plant growth, or freeze into ice that could persist for years before melting and beginning the cycle anew. The great mountain ranges that rise from our planet's surface owe their existence, in part, to solar energy working over geological timescales. While the immediate forces that push up mountains come from a movement of tectonic plates deep within the Earth, these plate movements are influenced by convection currents in the planet's interior that are ultimately driven by heat from radioactive decay and the sun's gravitational effects. Moreover, once mountains exist, solar energy begins the process of erosion that will eventually wear them down, creating sediments that will be transported by solar-powered wind and water systems to form new landscapes elsewhere. Picture an ancient mountain range as it first rises from the Earth's crust, its peaks gleaming in the sunlight that will immediately begin the long process of sculpting them into the forms we recognize today. Solar heating and cooling create thermal stresses that crack and fracture rock surfaces. Sunlight provides the energy for the water cycle that brings precipitation to high elevations, where it freezes in winter and melts in spring, creating the freeze-thaw cycles that gradually break rocks apart. Solar energy also powers the atmospheric circulation that brings weather systems to mountainous regions, delivering the wind, rain, and snow that slowly but persistently carve valleys and shape peaks. The differential heating of mountain slopes creates some of the most beautiful and complex local weather patterns on our planet. South-facing slopes in the northern hemisphere receive more direct sunlight and become warmer than north-facing slopes, creating temperature differences that drive local wind patterns and affect the types of vegetation that can grow in different locations. Mountain peaks create their own weather by forcing air masses to rise and cool, often triggering cloud formation and precipitation that wouldn't occur over flat terrain. Seasonal changes in the angle and intensity of sunlight create the great annual rhythms that govern life and landscape processes across much of our planet. As Earth orbits the Sun with its axis tilted at 23.5 degrees, different regions receive varying amounts of solar energy throughout the year, creating the succession of seasons that drive cycles of plant growth and dormancy, animal migration and reproduction, and the advance and retreat of ice and snow that reshape landscapes on annual timescales. Imagine the transformation of a temperate landscape as it responds to these seasonal changes in solar energy. Spring arrives as increasing day length and higher sun angles begin to warm the soil and air, melting winter snow and providing the energy needed for plants to begin their annual growth cycle. Summer brings maximum solar energy input, driving intense photosynthesis and creating the warm, moist conditions that support the year's peak biological activity. Autumn sees declining solar input as days grow shorter and the sun's angle decreases, triggering the spectacular color changes in deciduous leaves as plants prepare for winter dormancy. Winter's minimal solar energy creates the cold, often snow-covered conditions that slow or stop most biological processes while storing water in frozen form that will be released during the following spring's warming. The polar regions represent extreme examples of how seasonal variations in solar energy can shape landscapes and ecosystems. During polar summer, these regions receive continuous daylight for months, with the sun circling around the sky without setting, providing sustained energy input that can melt vast areas of ice and support brief but intense periods of biological activity. During polar winter, the sun disappears entirely for months, creating conditions so cold and dark that life virtually shuts down until the return of spring brings light and warmth back to these remote regions. Picture the Arctic tundra during the brief polar summer as continuous sunlight transforms a landscape that had been frozen and dormant for most of the year. The permafrost begins to thaw at its surface, creating boggy conditions that support rapid plant growth and attract migratory animals that have traveled thousands of miles to take advantage of this temporary abundance. The landscape becomes a hive of activity as plants rush to complete their annual growth and reproduction cycles before the return of winter darkness brings biological activity to a halt once again. Ocean currents represent another major way that solar energy shapes our planet's surface features and climate patterns. The heating and cooling of seawater by solar energy creates density differences that help drive the great circulation systems that transport warm water from tropical regions toward the poles and return cold water toward the equator. These currents carry enormous amounts of heat energy around the globe, moderating climate differences between regions and creating the relatively stable conditions that have allowed complex life to flourish. The Gulf Stream, which carries warm water from the tropical Atlantic northward along the eastern coast of North America and across to Europe, demonstrates how solar-powered ocean circulation can profoundly influence regional climates. This current transports roughly 100 times more heat energy than all of humanity's power consumption, warming the climate of northwestern Europe by several degrees and making possible the temperate conditions that support both natural ecosystems and human civilization at latitudes that would otherwise be much colder. Imagine the North Atlantic Ocean as this great river of warm water flows through it, carrying heat energy that was originally captured by sunlight in tropical seas. The current creates temperature gradients that influence weather patterns across thousands of miles, affecting everything from the formation of storms to the timing of seasonal changes. Marine ecosystems have evolved to take advantage of the nutrients and temperature conditions created by this current, creating rich fishing grounds and diverse biological communities that exist because of solar energy captured and transported across thousands of miles of ocean. The formation of weather systems themselves represents solar energy in action, creating the storms, wind patterns, and pressure systems that constantly reshape our planet's surface through erosion, sediment transport, and the distribution of precipitation. Hurricanes and typhoons are essentially heat engines powered by solar energy that has evaporated water from warm ocean surfaces, creating rotating storm systems that can transport enormous amounts of energy and water across vast distances before dissipating over land or cooler water. Desert formation represents another dramatic example of how solar energy patterns create distinctive landscape features. In regions where high-pressure systems created by global circulation patterns prevent cloud formation and precipitation, intense solar heating creates some of the most extreme environments on our planet. These landscapes, shaped by constant sun and minimal water, develop unique features like sand dunes, salt flats, and rocky formations that reflect the powerful influence of concentrated solar energy working over long time periods. Picture the Sahara Desert as an example of a solar-sculpted landscape, where intense heating and minimal precipitation have created a vast expanse of sand and rock that stretches across thousands of miles. The daily heating and cooling cycles create strong wind patterns that constantly reshape sand dunes, while the lack of vegetation allows erosion processes to work directly on exposed rock and sediment. Even this apparently barren landscape pulses with solar energy as temperature differences between day and night create thermal effects that influence everything from local wind patterns to the gradual weathering of rock formations. Glacial systems represent the opposite extreme, where reduced solar energy input or enhanced reflection of sunlight creates conditions cold enough for ice to accumulate over long periods. These massive ice formations, some of which contain water that fell as snow thousands of years ago, act as both repositories of solar energy history and powerful sculptors of landscape as they advance and retreat in response to climate changes driven by variations in solar energy input. The great ice sheets that have repeatedly formed and melted throughout Earth's history demonstrate how changes in solar energy patterns can create landscape features on continental scales. As these ice masses advance, they scour the landscape beneath them, carving valleys, transporting sediments, and creating the topographic features that influence drainage patterns and ecosystem development long after the ice has retreated. When they melt, they release enormous volumes of water that can dramatically reshape coastlines and river systems. As you rest here tonight, consider that every landscape feature visible from your window, every hill and valley, every river and lake, every forest and field, bears the signature of solar energy working over timescales that range from moments to millions of years. The gentle breeze that might stir your curtains is powered by solar heating. The water that flows in nearby streams was lifted from distant oceans by solar energy, and the soil that supports the plants in your environment was created through countless cycles of solar-powered weathering and biological activity. The daily rhythm of heating and cooling that you experience as day turns to night reflects the same fundamental solar energy cycles that have been shaping our planet's surface for billions of years, connecting your immediate environment to the vast global systems that make Earth a dynamic, ever-changing world where light serves as both the energy source for life and the sculptor of the landscapes where that life unfolds. In your peaceful rest tonight, you participate in the same daily cycle of solar energy that drives all the great circulation systems of our planet, from the gentle local breezes to the vast ocean currents that transport heat around the globe, all powered by the inexhaustible energy of our sun and the countless ways that light interacts with matter to create the beautiful, complex world we call home. Perhaps no aspect of light's influence on life is more intimate and immediate than the way it governs the internal rhythms that pulse through every living thing on our planet. From the smallest bacteria to the largest mammals, from the simplest algae to the most complex flowering plants, virtually all forms of life have evolved sophisticated internal clocks that synchronize their biological processes with the daily cycle of light and darkness that has remained constant throughout Earth's history. This ancient dance of day and night has become so fundamental to life that it continues to guide our biology even when we're separated from natural light cycles, connecting us to rhythms that are literally written into our genes. Picture the early Earth during those primordial times when life was just beginning to organize itself into more complex forms. Even then, the rotation of our planet created a reliable 24-hour cycle of illumination and darkness that provided one of the most predictable environmental cues available to developing organisms. Natural selection quickly favored those creatures that could anticipate and prepare for these daily changes rather than simply reacting to them after they occurred. The ability to predict sunrise and sunset, to prepare for the coming of dawn or the approach of night, provided such significant survival advantages that internal biological clocks evolved independently in virtually every major group of living things. These biological timepieces, which scientists call circadian rhythms, operate through incredibly sophisticated molecular machinery that rivals the precision of any human-made clock. Deep within the cells of virtually every organism, specialized genes turn on and off in carefully orchestrated cycles that take approximately 24 hours to complete. These genetic oscillators create rhythmic changes in cellular chemistry that influence everything from metabolism and growth to reproduction and behavior, ensuring that different biological processes occur at the optimal times of day for maximum efficiency and survival benefit. Imagine the molecular clockwork operating within your own cells as you rest here tonight, even though you may be completely unaware of it. Thousands of genes throughout your body are following their ancient rhythmic patterns, some reaching peak activity during the night hours, while others prepare for the increased demands of daytime activity. Your liver is busy processing and storing the nutrients from your last meal. Your immune system is ramping up its activity to fight off infections while you sleep, and your brain is consolidating memories and clearing away metabolic waste products that accumulated during the day. The evolution of these internal clocks represents one of the most remarkable examples of how life has learned to harness the predictable aspects of its environment for survival advantage. Rather than simply responding to light when it appears or darkness when it falls, organisms with well-developed circadian rhythms can anticipate these changes and adjust their physiology accordingly. A flower can begin opening its petals before dawn so that it's fully prepared to receive pollinating insects at first light. A nocturnal animal can start becoming alert and active before sunset so that it's ready to hunt as soon as darkness provides cover from its own predators. The precision of these biological clocks is truly extraordinary, even when kept in constant darkness or constant light for days or weeks. Most organisms continue to follow approximately 24-hour cycles in their biological activities. This demonstrates that the clockwork is truly internal, not simply a passive response to external light cues, though it can be fine-tuned and synchronized by exposure to the daily light-dark cycle. The word circadian itself means about a day, reflecting the fact that these internal rhythms run slightly longer or shorter than exactly 24 hours when isolated from external time cues. Picture a simple, single-celled organism floating in the ancient oceans as it developed some of the earliest versions of these internal clocks. During the day, when sunlight was available for photosynthesis, the cell would activate the molecular machinery needed to capture light energy and convert carbon dioxide into organic compounds. At night, when photosynthesis was impossible, the same cell would shift its focus to other activities like growth, reproduction, or cellular maintenance. This basic pattern of alternating between energy capture and energy utilization became so fundamental to life that it persists in virtually all living things today. As life became more complex and diverse, circadian rhythms evolved to control an ever-expanding array of biological processes. Plants developed internal clocks that governed not only photosynthesis, but also the opening and closing of flowers, the release of fragrances that attract pollinators, and the timing of reproductive processes. Many flowers open only at specific times of day when their preferred pollinators are most active, while others release their pollen during particular hours when humidity and wind conditions are optimal for dispersal. The relationship between circadian rhythms and behavior became increasingly sophisticated as complex animals evolved. Many species developed elaborate daily routines that were precisely timed to take advantage of optimal conditions for different activities. Some animals became strictly diurnal, concentrating all their active behaviors during daylight hours when their vision-based hunting or foraging strategies were most effective. Others became nocturnal, using the cover of darkness to avoid predators or to hunt prey that were less alert at night. Still, others adopted crepuscular lifestyles, becoming most active during the twilight hours of dawn and dusk when lighting conditions provided the perfect balance between visibility and concealment. Imagine a typical dawn in an ancient forest as these various circadian rhythms played out across the ecosystem. As the first light appeared in the eastern sky, diurnal birds would begin their morning songs. Each species timed to start at a slightly different moment to avoid acoustic interference with competitors. Flowers that had remained closed during the night would begin opening their petals in preparation for the day's pollinating visitors. Nocturnal animals would be seeking their final feeding opportunities before retreating to sheltered locations for daytime rest, while diurnal species would be emerging from their nighttime refuges and beginning their daily foraging activities. The evolution of complex eyes and sophisticated visual systems added new dimensions to these circadian responses. Many animals develop the ability to detect the subtle changes in light quality that occur during twilight transitions, allowing them to fine-tune their daily activity patterns based on precise measurements of dawn and dusk timing. The blue light that predominates during early morning hours became a particularly important signal for synchronizing internal clocks, while the red light of sunset provided information about the approaching night. Seasonal changes in day length created additional opportunities for biological rhythms to influence survival strategies. Many organisms evolved the ability to use changing patterns of daylight and darkness to anticipate seasonal transitions and adjust their behavior accordingly. Migration timing, reproductive cycles, and seasonal changes in coat color or metabolic rate became linked to circadian clock mechanisms that could track not only daily light-dark cycles, but also the gradual changes in day length that mark the progression of seasons. Picture a migratory bird as it prepared for its annual journey to distant wintering grounds, its internal clock system carefully monitoring the gradually shortening days of late summer. Long before food availability or weather conditions would force the journey, the bird's circadian rhythms would begin triggering hormonal changes that increased fat storage, enhanced navigation abilities, and created the restless behavior that would eventually drive it to begin its epic migration. These preparatory changes, initiated by light-sensitive clock mechanisms, gave migrating animals crucial advantages in timing their journeys to coincide with optimal travel conditions. The molecular mechanisms underlying circadian rhythms are remarkably similar across vastly different forms of life, suggesting that these clock systems evolved very early in the history of life and have been maintained with relatively little change for billions of years. The core clock genes found in plants show striking similarities to those found in animals, despite the fact that these two major groups of organisms diverged from their common ancestor over a billion years ago. This conservation suggests that circadian timing provided such fundamental survival advantages that evolution has preserved the basic clockwork mechanisms while allowing them to control an ever-expanding variety of biological processes. Modern research has revealed that disruptions to natural circadian rhythms can have profound effects on health and well-being in virtually all organisms studied. When plants are kept under artificial lighting that doesn't follow natural day-night cycles, they often show reduced growth, altered flower and fruit production, and increased susceptibility to diseases. Animals subjected to irregular lighting patterns may experience disrupted sleep, altered immune function, and changes in behavior that can affect their survival in natural environments. As human civilization has developed artificial lighting that allows us to extend our active hours well beyond sunset, we've inadvertently conducted a vast experiment in circadian disruption that affects not only our own biology, but also the countless other species that share our increasingly illuminated world. The gentle rhythms that evolved over billions of years to synchronize life with the natural cycles of day and night now must contend with the constant glow of electric lights that can confuse biological clocks and disrupt the timing of essential biological processes. Yet, even in our modern world of artificial illumination, the ancient power of natural light cycles continues to influence our biology in ways we're only beginning to understand. Exposure to bright light during morning hours can help maintain healthy circadian rhythms, while avoiding bright lights in the evening hours allows our internal clocks to prepare properly for restorative sleep. The same light-sensitive mechanisms that evolved in our distant ancestors continue to operate in our modern bodies, connecting us to rhythms that are literally as old as life itself. As the long story of vision's evolution reached its culmination in the sophisticated visual systems of primates, something extraordinary began to happen that would distinguish human sight from all the remarkable visual adaptations that had preceded it. While our eyes themselves are masterpieces of biological engineering that rival those of other advanced animals, what truly sets human vision apart is not the physical structure of our visual systems, but rather the way our brains learn to interpret and use visual information to create culture, art, technology, and the complex symbolic worlds that define human civilization. In learning to see, we learn to imagine, and in learning to imagine, we began to reshape the world itself according to our visual dreams and inspirations. Picture our early human ancestors as they emerged from the forests of Africa and began to explore the open savannas that would become the cradle of human civilization. Their eyes, inherited from millions of years of primate evolution, were already sophisticated instruments capable of excellent color discrimination, sharp visual acuity, and sophisticated depth perception. These visual capabilities had evolved for life in forest canopies, where the ability to judge distances accurately and distinguish ripe fruits against green foliage provided crucial survival advantages. But as humans began to inhabit more open environments, these same visual skills would be applied to entirely new challenges and opportunities. The transition to upright walking gave human vision a new perspective on the world, literally. Standing tall on two legs provided a higher vantage point that extended visual range and allowed early humans to spot both opportunities and threats across the open landscapes they were beginning to inhabit. This elevated viewpoint also enabled new forms of visual communication, as gestures and body language became visible across greater distances, laying the foundation for the complex nonverbal communication systems that would eventually support the development of language and culture. The human visual system's exceptional ability to detect and track movement became crucial for survival on the African savannas, where both predators and prey were often first detected as moving shapes against the landscape background. Our ancestors developed the ability to distinguish between different types of movement patterns, the distinctive gait of various animals, the swaying of grass that might indicate approaching danger, or the subtle movements that could reveal hidden prey or predators. This visual sensitivity to movement would later be channeled into artistic expression as humans learned to capture and represent motion in their cave paintings and other early art forms. Imagine one of these early humans crouched beside a waterhole at dawn, their eyes scanning the surrounding landscape for signs of the animals they hoped to hunt or the predators they needed to avoid. Their visual system was processing an enormous amount of information simultaneously, tracking multiple moving objects, assessing distances and angles for potential tool use, monitoring the behavior of other group members, and maintaining awareness of environmental changes that might signal weather shifts or other important developments. This constant visual multitasking helped develop the cognitive flexibility that would eventually enable humans to use their sight for increasingly complex and abstract purposes. The development of tool use added entirely new dimensions to human visual experience. Early stone tools required sophisticated visual motor coordination to manufacture, with toolmakers needing to visualize the desired end product and plan the sequence of strikes needed to shape raw stone into functional implements. This required a type of visual thinking that went beyond immediate perception to include mental imagery, spatial reasoning, and the ability to imagine objects that didn't yet exist but could be created through skilled manipulation of materials. Picture an early human toolmaker examining a piece of raw flint, their eyes moving over its surface as they mentally map the natural fracture lines and envision the tool that could be released from within the stone. This visual planning process required the ability to see not just what was present, but what was possible, a cognitive leap that marked the beginning of human creativity and technological innovation. The same visual spatial skills that guided tool manufacture would eventually be applied to architecture, engineering, and all the technical achievements that characterize human civilization. The use of fire added another transformative dimension to human visual experience. The ability to create and control fire extended the useful hours of human vision into the nighttime, creating new opportunities for social interaction, tool manufacture, and food preparation that would have been impossible in natural darkness. The warm, flickering light of fires also created the first human-controlled lighting environments, allowing our ancestors to experiment with different visual conditions and begin developing the aesthetic sensibilities that would eventually flower into art and decoration. Imagine a group of early humans gathered around a fire as darkness fell over their camp. In the dancing light of the flames, faces took on new expressions and meanings. Shadows created shapes that might inspire stories or artistic visions, and the interplay of light and darkness provided a rich sensory environment that stimulated imagination and creativity. This firelit world was humanity's first step toward creating artificial visual environments that could enhance and extend natural perception. The development of language created unprecedented connections between human vision and symbolic thinking. As humans learned to associate visual symbols with spoken words and abstract concepts, they began developing the first writing systems that could preserve and transmit information across time and space. These early pictographic and ideographic writing systems relied heavily on visual recognition and memory, creating new selective pressures that favored individuals with enhanced visual processing abilities and symbolic reasoning skills. Picture the moment when an early human first realized that marks made on stone or clay could represent objects, sounds, or ideas that weren't physically present. This visual symbolic breakthrough opened up infinite possibilities for human communication and knowledge preservation, allowing information to be stored outside individual human memory and shared across generations. The visual processing of written symbols would become one of the most important applications of human sight, eventually enabling the accumulation of knowledge that makes modern civilization possible. The creation of art represents perhaps the most uniquely human application of visual capabilities. While other animals occasionally engage in behaviors that produce visually appealing results, humans are the only species that systematically creates visual representations for purely aesthetic or symbolic purposes. The cave paintings of Lascaux and Altamira demonstrate that by at least 30,000 years ago, humans had developed not only the technical skills needed to create sophisticated visual art, but also the cognitive abilities required to appreciate and value beauty for its own sake. These early artistic achievements reveal visual capabilities that go far beyond basic survival needs. The artists who created these cave paintings possessed sophisticated understanding of perspective, proportion, and visual composition that allowed them to create recognizable and emotionally powerful representations of the animals and landscapes that dominated their world. They had learned to see not just with their eyes, but with their imagination, creating visual experiences that could evoke emotions and convey meaning in ways that transcended immediate practical utility. The development of agriculture created new relationships between human vision and the landscape that would fundamentally change how our species perceived and interacted with the natural world. Farmers needed to develop keen visual skills for assessing soil conditions, plant health, weather patterns, and the countless other visual cues that determine agricultural success. This close observation of natural cycles and plant behavior led to increasingly sophisticated understanding of ecological relationships and seasonal patterns that could be applied to crop management and food production. Picture an early farmer walking through their fields at dawn, their eyes trained to notice subtle differences in plant color that might indicate nutrient deficiencies, pest problems, or optimal harvest timing. This agricultural vision required a different type of visual expertise than hunting or gathering, focusing on small details and gradual changes rather than movement and immediate spatial relationships. The development of these observational skills contributed to the growing human understanding of natural processes that would eventually develop into scientific methodology. The rise of cities and complex societies created entirely new visual environments that challenged and expanded human perceptual capabilities. Urban life required the ability to navigate complex spatial layouts, recognize large numbers of individual people, and process the visual complexity of crowded, architecturally diverse environments. These challenges drove the development of new forms of visual culture, including architectural styles, urban planning principles, and decorative arts that transformed human settlements into rich visual experiences. The invention of writing systems led to the development of visual arts that were specifically designed to enhance and support written communication. Illuminated manuscripts, decorative calligraphy, and illustrated text created new relationships between visual and verbal information that enriched both forms of communication. These developments demonstrated the uniquely human ability to integrate different types of symbolic representation into unified cultural expressions that could convey complex meanings and emotions. Picture a medieval monk working by candlelight to create an illuminated manuscript, their eyes moving between the written text and the decorative borders they were painting to accompany it. This type of visual work required extraordinary precision and aesthetic sensitivity, along with the ability to coordinate complex visual motor skills over extended periods. The results were visual masterpieces that elevated functional writing into high art, demonstrating the human capacity to find beauty and meaning in even practical activities. The development of scientific observation techniques represented another uniquely human application of visual capabilities. As humans learned to use tools like telescopes and microscopes to extend their natural vision, they discovered entire worlds of visual experience that had been previously invisible. These technological extensions of human sight opened up new frontiers for visual exploration and understanding that continue to expand our knowledge of the universe today. The invention of photography and later film and digital imaging created revolutionary new possibilities for capturing, preserving, and sharing visual experiences. These technologies allowed humans to see their world in entirely new ways, from high-speed photography that revealed the beauty of motion too fast for natural perception to time-lapse imagery that compressed slow changes into visible sequences. Photography also democratized visual art, making it possible for anyone to create and share compelling visual representations. As you rest here tonight, your own eyes represent the culmination of this remarkable journey, from simple light detection to the sophisticated visual culture that characterizes modern human civilization. Every time you read these words, appreciate a work of art, navigate through your environment, or simply enjoy the visual beauty of your surroundings, you're using capabilities that connect you directly to the entire history of vision's evolution, while also participating in the uniquely human adventure of visual culture and creativity. Your ability to see meaning in visual symbols, to appreciate beauty for its own sake, and to imagine visual possibilities that don't yet exist but could be created represents the current frontier of vision's evolution. In your dreams tonight, your visual cortex may continue processing and integrating the day's visual experiences, creating new combinations and possibilities that reflect the endless human capacity for visual imagination and creativity that has transformed not only how we see the world, but how the world itself appears through human eyes and human vision. As we reach the end of our gentle journey through the story of how light built the world you see, it's worth pausing to consider the profound continuity that connects every aspect of this remarkable tale. From the first photons that escaped the cosmic fog of creation to the light entering your eyes right now as you rest here tonight, there has been an unbroken chain of illumination that links the birth of the universe to this very moment of peaceful contemplation. The same fundamental interactions between light and matter that lit the first stars continue to power the vision that allows you to perceive beauty. The photosynthesis that creates the oxygen you breathe, and the gentle daily rhythms that guide your body toward restful sleep. Picture the universe as it exists tonight, filled with countless points of light scattered across vast distances of space and time. Every star you might glimpse through your window represents a nuclear furnace, converting matter into energy and light, continuing the stellar traditions that began billions of years ago when the first massive stars ignited in the cosmic darkness. The light from these distant suns carries the same fundamental properties as the photons that first enabled vision in ancient seas, that powered the transformation of Earth's atmosphere, and that continue to paint the landscapes and weather patterns of our dynamic planet. The remarkable story we've explored together reveals light not as a simple physical phenomenon, but as the fundamental architect of complexity, beauty, and life itself. Through the patient work of evolution operating over geological timescales, light has guided the development of increasingly sophisticated biological systems that could not only detect and use electromagnetic radiation, but eventually learn to appreciate its aesthetic qualities and harness its power for creating the technological marvels that characterize human civilization. In your own daily experience, you participate in all the great themes of this cosmic story. Every breath you take connects you to the ancient process of photosynthesis that transformed our planet's atmosphere and continues to generate the oxygen that sustains complex life. Every moment of vision links you to the remarkable evolutionary journey that led from simple chemical responses to light in primitive bacteria to the sophisticated visual systems that allow you to read these words and appreciate the beauty of your world. The circadian rhythms that guide your body towards sleep tonight echo the same fundamental cycles of light and darkness that have governed life on Earth for billions of years. As your metabolism slows and your visual system gradually reduces its activity, you participate in the ancient dance of day and night that has provided the temporal framework for virtually all biological processes since life first learned to anticipate and prepare for the daily changes in illumination that mark the passage of time. Picture yourself as part of this vast, interconnected web of light-dependent processes that spans from the molecular clockwork operating within your cells to the great circulation systems that distribute solar energy around our planet. Your comfortable rest tonight is made possible by countless light-powered processes working together. The photosynthetic organisms that created the oxygen-rich atmosphere you breathe, the solar-driven weather systems that bring water to the plants that produce your food, and the visual capabilities that allow you to navigate safely through your illuminated world. The eternal glow that connects all these processes reminds us that light is not just something we observe from outside, but something we are intimately part of. The carbon atoms in your body were forged in the nuclear fires of ancient stars. The energy that powers your thoughts and movements ultimately derives from sunlight captured by photosynthetic organisms, and the visual experiences that enrich your life depend on the same electromagnetic radiation that has been shaping our universe since its earliest moments. As you drift toward deeper rest, your brain may continue to process visual memories and experiences, creating the dreams that demonstrate our remarkable human ability to generate internal light experiences even in darkness. These dream visions connect you to the same neural pathways that evolve to interpret external light, showing how thoroughly light and vision have become integrated into the very essence of what makes us human. Tonight, as countless stars continue their ancient work of converting matter into light and energy, as photosynthetic organisms around the globe prepare for tomorrow's capture of solar energy, And as the eternal rhythms of day and night continue their patient guidance of life's processes, you can rest peacefully knowing that you are part of the most beautiful and complex story ever told. The story of how light built the world you see, continues to sustain the life you live, and will forever connect you to the luminous cosmos that surrounds and includes us all. Sleep well, knowing that the gentle glow of starlight, the promise of tomorrow's sunrise, and the eternal dance of electromagnetic radiation that powers all life will continue their work while you rest, maintaining the illuminated world that welcomes you back each morning to participate once again in the ongoing story of light, life, and the endless beauty they create together.